So good morning, everyone. I have a few comments to make before I start. This is, you got some notes from my lectures. There are, unfortunately, when I went over the lectures for preparation, there are some typos. And so my first comment is pay attention to the lecture because some of them have been corrected. Unfortunately, there's always typos, and sometimes I catch them when I speak, sometimes I don't. I have an advice for you in general. Don't ever take a certain equation for granted in some form in a paper. Try to go to the origin and make sure that that's the correct one, because even when things have been cited, sometimes they're not cited properly. So this is an important advice to using any existing formula expression and so on. Second comment I want to make is a few things about combustion theory. So the aim of combustion theory is to try to understand the underlying mechanism of various combustion behavior. And it requires a broad knowledge, as you see, of fluid mechanics, mass transfer, chemistry, multi-component mixture, which is typical in all combustion systems, thermodynamics, heat transfer. Of course, I will not and cannot cover everything, so the assumption is that you have some knowledge of those. And through the lecture, you'll be able to pick at least some of the ideas, the concepts, and then you would have to look into the literature for more detail of those. Dealing with combustion system, we are typically dealing with complex system of partial differential equations. And at the most part, we understand or we know the general equation that describe combustion system, but to solve this equation is the difficult part. And so there are, of course, various ways or approach to do that. Some of them is, of course, through computation or simulation, but even there are assumption and approximation made in trying to solve the equation. The direction or the path that I will describe is more in theory. In theory, what we try is to simplify the equation by choosing or selecting the most important parameters that affect a certain behavior, neglecting those that seem secondary. And the advantage is that we can either derive some analytical expression or semi-analytical expression or a simpler system of equation that can be solved quickly nowadays on a laptop without a big computational need and knowledge. So that's the advantage, but the aim is to provide some parametric dependence on the various parameters in the problem to identify some of the key physical mechanism of a given process, sometimes to explain some experimental observation or even to guide the experimental work, and also to provide guide to the numerical simulation, because if you have an idea a priori of what the system should look, at least in some limited cases, it helps in constructing a proper code or proper numerical methodology to solve the problem, and you can use those simpler example or simpler system as a validation of your numerical code. So those are some key things. Already Professor Lowe mentioned the importance of theory in predicting combustion system. It goes along with simulation and experiment, and at the end I will just tell you what I plan to do this week. So I will start today primarily with the conservation equation, it's important to understand, I'm not going to derive them from start, but I will use a plausible idea or plausible way of expressing or deriving this equation, assuming that you have some knowledge of fluid mechanics of a pure substance, in other words, without the mixing and the various multi-component aspects. And the importance of knowing those or understanding those equations, it's even when you want to solve them numerically to understand what the different terms in the equation come from, what assumptions were made, and so on. We will talk tomorrow mostly about premixed flame, the planar flame, and some hydrodynamic theory that describe multidimensional flame, the notion of a flame stretch, probably a parameter that you all have heard of, Markstein length, what it is, where it comes from, and so on. Then we will talk on the third day about combustion in closed vessel, where the physics is a bit different than when you describe just a flame propagating in open space. And and then we will start on diffusion flames. Unfortunately, I cannot do a single day on every topic, so we will start day 3 with diffusion flame, move to day 4, talk about edge flame and droplet combustion. All of them are diffusion flames or combustion of non-premixed system. And finally, the last day, we'll talk about flame instabilities and some ideas of turbulent flame speed. Not talking about turbulence in general. I assume you have a different lecture on that. So let me start right up to the first topic. Don't allow. Okay. So as I said, we will try to talk about the conservation equation for multi-component chemically reacting mixture. And as I just said earlier, the idea is that you should have some knowledge, so I will briefly review the governing equation for a pure substance. So what we have, the first one is a conservation of mass. So the equation is, unfortunately, I don't have a pointer. My pointer doesn't work, so maybe I'll get one later on. So you see the equation, the conservation equation or the continuity equation, which is on the left, the conservation of mass, can also be equivalently written as on the right. The capital D by dt is known as the material derivative. I'm sure that most of you know what it is, but I'm still reviewing it, at least in my words, which is the time rate of change, essentially, of a fluid particle, following a fluid particle. So this is the conservation of mass. Just few comments. When the time rate of change of the density of a particle is relatively small, as indicated there, then essentially the second term is equal to 0, or the divergence of V equal to 0. We refer that to as an incompressible fluid. Essentially, the reciprocal of the density is the specific volume, so the divergence of V is the rate of compression or expansion of a fluid particle. The next conservation statement is conservation of mass, which is essentially Newton's law. So what you have is the density times acceleration of a particle, the time rate of change of its velocity, is equal to all the forces acting on the particle. Some of the forces are surface forces that are acting from surrounding particles, and sigma here is known as the stress tensor. It's a tensor, has 9 components, but due to some other argument, it is really a symmetric tensor, so it really have only 6 independent independent components. And the last term is rho, the density, times the body force acceleration. typically it's gravity, but it doesn't have to be only gravity, it can be electrical forces. It's forces that are acting on the entire volume of the particle. So this is the second conservation law. The third conservation law is conservation of energy, and I want to write it first in terms of the total energy, ET, which consists of the internal energy plus the kinetic energy, half V squared. And then the time rate of change of the energy of a fluid particle, which is the left part of the equation, is equal to all the work, first the rate of the work done on the fluid particle by both body and surface forces. So the first term is due to the surface forces, the second term due to the body forces, indicated F being the body force per unit mass, and the rate of heat transfer to the fluid, which is denoted by Q is the heat flux vector, so it's the divergence of the heat flux. Now, there is a convention associated with this, which is the heat transfer to the fluid is positive. Okay, I will indicate that later as well. Now, it's convenient in fluid mechanics to extract from the total energy the kinetic energy. Now, the way that you do this, since we have an equation for the velocity, you can multiply it by V itself, so you have a quantity like V squared, which is the kinetic energy, and that equation is essentially here. And so when you extract it from the top, you get an equation that involves only the internal energy, and there are two terms coming from the stress tensor that together they operate in something which is referred to as a contraction. So the contraction of two tensors is essentially by component the double sum of Aij, Cij. A double sum because usually when you use indices, when the index appears twice in the expression, it's had to be summed over all the whatever that index runs. So this goes 1 to 3, 1 to 3, so it's a double summation. So that double summation is essentially expressed here, and then the heat flux or the heat transfer to the fluid. So this is the equation that we will more focus on. However, very often we use a slightly different thermodynamic property. Instead of internal energy, we use the enthalpy. So we will talk about that in a few minutes. But before this, as you have noticed in all these equations, there are properties or terms that are not defined, like, for example, the stress tensor or the heat flux, Q. And so we need some additional laws to express those terms. Those are often referred to as constitutive laws because they are not statement of conservation. Those are laws that come from experiment, from empirical knowledge. And so, for example, the stress tensor is usually in most fluids, but not all, is related to, or is linearly related to the rate of strain, and the rate of strain is essentially affected by the velocity field. Now, I said not all. For example, ketchup is not a Newtonian fluid, doesn't have that behavior. And so I have a more complex relation, but it's not of concern in combustion. So the expression that the stress tensor sigma is related to the rate of strain, it's usually expressed in this form, and it's known as a Newtonian fluid. P is the pressure, I is the unit tensor, so that's the first term on the right. And then you have two terms that are multiplied by some coefficient, mu and mu hat. Mu is the shear viscosity, which can be measured experimentally, and the term in the middle, grad V and grad V transpose, are essentially the rate of strain. So together they correspond to the rate of strain of a fluid particle. The next term is related. Remember that divergence V is the rate of compression, expansion of a fluid particle, so it's related to that. And the coefficient mu hat is often written as kappa minus 2/3 mu. Kappa is known as the bulk viscosity, and in most situation, again, most situation is very small and negligible, and it's typically taken as equal to 0. Mu hat is known as the second viscosity coefficient, and there are very few examples, perhaps in combustion, where that turn out to be important. Again, remember, this is a constitutive relation, so mu hat are determined empirically for different fluids. So this is one of the unknown. If you plug that in the momentum equation, you're going to get that the time rate of change of the mass times acceleration, time rate of change of the velocity, is related to the gradient of the pressure and the viscous term. In general, mu is not a constant, and so that's going to be the divergence of the viscous stresses. And the last term, as we had before, is the body force. If we plug that in the energy equation, remember there was this term in the energy equation that came from the stress tensor, we get a term which is often referred to as the viscous heating, or which is denoted here by phi, or the dissipation parameter, and phi can be easily computed again by the double sum written here. We will come back to it and to see its importance in combustion system. So again, you have this term which comes from the work done on the fluid particle, the viscous heating, and the heat flux as before. We are still left to determine Q, and Q, the heat flux, which again is, we need a constitutive law for it. We usually typically assume the Fourier law of heat conduction. So, well, I mean, there may be more things involved in the heat flux, such as radiation, but if we neglect radiation for now, I think at some point I included it, or at least temporarily included it. You will see it later. Then the Fourier law is essentially that the heat flux is proportional to the temperature gradient. So heat is transferred from hot to cold, and hence you have the negative sign, and it depends on the material property, which is lambda, which is known as the conductivity. So when you plug that into the equation, here is the energy equation that end up. So we spoke about the different terms. Now there are still quantities that need to be determined, such as the pressure, the relation to the temperature, and so on. So we need some thermodynamic relation or some discussion of thermodynamics. And in thermodynamics, for a pure substance, it's known that every property depends on only two other properties. So for example, state of the gas is uniquely determined by two variables. So for example, the pressure depends on density and temperature. The internal energy can be written as pressure and temperature. Of course, you can relate it to density and temperature, any two other variables. So we need to identify those relations in order to plug them into the equation and have a complete system. Also, there are some other thermodynamic variables that appear usually of interest or in writing the equation. One of them is the enthalpy, and the enthalpy is defined as the internal energy plus P over rho. And the other one is the entropy, which one way to determine it is from what is known in thermodynamics as a TdS relation, essentially T times the change in entropy is the change in enthalpy plus change in pressure divided by density. So those are the relation that we want to use to further expand or write our governing equation. The first one is we often, instead of using the internal energy for the energy conservation, we use enthalpy. And the relation between the two, which is written here, required to rewrite the time rate of change of the internal energy, which it's easy to do using this relation. Essentially, change in H, change in E, plus then you have the derivative of the ratio. And when you do this and use the continuity equation to replace d rho by dt, you can write the equation in that form. Note that the only difference is the way that the body, the work done on the fluid element appear here. It appears at dp dt, the material derivative of the pressure, whereas in the first equation it appeared slightly in a different form. The remaining things are the same. The dissipation term, which is heat produced by viscous friction, and the heat conduction term. Next, we need to relate the different state variables. And of course, we're going to assume for simplicity an ideal gas. It doesn't mean that all combustion system behaves that way, but that's typically the simplest one that you can use. And so P is equal to rho RT divided by W. R is the gas constant, universal gas constant written on top. W is the molecular weight. Now, for an ideal gas, we further have we further know that the internal energy depend on temperature only. And thank you. And as a result, we can see that the enthalpy therefore depend also on the temperature only. So both the internal energy and enthalpy depend on the temperature only. The next thing that we want to define are the so-called specific heat. And there are two specific heat, one at constant pressure, one at constant volume. And so they are essentially defined from this equation. The derivative in time of H is Cp, dE by dt is Cv. And essentially, you can integrate that relation and get, thank you. And this move forward. Okay, and so we will play with this and see how it works. So the enthalpy H is some integration constant, which is usually a reference value, plus the integral of Cp, since Cp depends on temperature, the integral of Cp from the reference temperature to T. Similarly, E is a reference value plus the integral of Cv from the reference temperature to T. Now, in a pure substance, we are only interested, well, in general, in a fluid problem, we are only interested in the change in enthalpy. So in a pure substance, the reference value doesn't matter. You choose anything you want because it doesn't enter your equation. We're going to see that when you have a mixture, the story is a little bit different, and that's important to understand the difference. So if we, so those are the relations. We can also Since we know that H and E are related as such, then the Cp and Cv are also related, and since the gas constant is always positive, then Cp is always greater than Cv. Another property that show up is usually the ratio of specific heat, Cp over Cv, and it's usually denoted by gamma, and it's bigger than 1, and clearly for that purpose. And if one write the Cp and Cv in terms of gamma, it's a straightforward algebraic calculation. Now, in all my lecture this week, I tried, and I say I tried, to keep my notation the same. Occasionally, there may have been some small changes, but I'll emphasize that when it comes. One last thing is the speed of sound for an isentropic flow, which is adiabatic and reversible. Then the entropy does not change, so ds is equal to 0, and so we have another relation that relate the enthalpy H with density and pressure. So we have two relations. One dH is dP over rho, one dH is Cp dt, and from those two you can obtain the so-called isentropic relation, which is P rho to the minus gamma is always a constant, the gamma being the ratio of specific heat. And finally, the speed of sound is defined as the ratio of pressure to density changes under isentropic condition. And so it's dP d rho keeping S constant, that's the notation here. And since you can integrate that from the isentropic relation, you get that the speed of sound is gamma P over rho, or gamma RT. The bar here indicated it's a specific gas constant, not the universal gas constant. So, of course, speed of sound depends on the material that you use. Now, let's see if I know how to do this. No, that didn't work. This didn't work. Okay, so we use this only as a pointer. So in short, we have derived equation for a pure substance, conservation of mass, conservation of momentum, energy in terms of the enthalpy, and the equation of state, where all the where H, the enthalpy is given by Cp dt, and so there are of course properties that remain to be determined, like viscosity, conductivity, specific heat, molecular weight, and so on. Those are known experimentally. Apart from that, we have 7 equations, and we have 7 unknowns. 7 equations because there's one. This is a vector equation, so it's three components. So it's 4, 5, 6, 7, and the unknowns is 3, 4, 5, 6, 7. So we have 7 equations, 7 unknowns. So mathematically, we have a closed system. Now, the big question is, what happens when we have a mixture? And that's really, I started with those equations in order to use that as a basis to derive equation, or not really derive, but write equation for a mixture. So if we have a gas mixture that consists of m species, I will denote the species I equal 1, 2 to n. So the index I is the identifying certain species. Then there are a few things that we need first to define. The first thing is a concentration of species I inside the volume, which is defined as the number of moles of the species I per unit volume. So Ci is the notation of the concentration, number of moles, Ni divided by the volume. And then we can talk about the mass of the molecules of species I, which will be Mi. It's the number of moles multiplied by the molecular weight of species I, and the density of species I, which is the mass divided by the volume. Okay? So everything here is for the species I. Then we are interested to talk about the density of the entire mixture. And so the density of the entire mixture is essentially the sum of all the densities. I goes from 1 to n, which can be also written as the mass divided by the volume from the definition. And the total mass is m, so it's a total mass divided by the total volume, which is the density of the mixture, which is denoted by rho. So rho is the density of the mixture. It's written the sum of all the rho I. We can now write an expression for the concentration of the mixture, which is going to be the sum of all the concentrations Ci, which is the number of moles Ni divided by V summed on all I, and the number of all the moles Ni is the total number N, so it's N over V, so this is the concentration of the mixture. So we have now the mass or the density of the mixture, the concentration of the mixture. That helps us to define mole fraction or mass fraction. So mole fraction will be the concentration of species I divided by the total concentration. So it's the fractional amount, okay? Or it can be written as Ni over N, because the only difference is dividing by Wi, or whatever we have to divide, by V, sorry. So Xi are the mole fraction, and of course there are numbers between 0 and 1. And when you sum all Xi, the sum of all Ni is N, N over N is 1, so clearly the sum must be equal to 1. Similarly, one can define the mass fraction, which is denoted by Yi. It's a common notation, by the way, which is the mass Mi divided by M. Again, because I can divide by the volume, I can write it as the density, rho I over rho. So we have the mole fraction and the mass fraction. Again, the mass fractions are numbers between 0 and 1. And when you sum over all I, the sum of Yi is equal to 1. So the sum of Xi is 1, sum of Yi is 1. There must be a relation between Xi and Yi, which we will examine in a few minutes. But before that, if we use the fact that M is the total mass of the mixture, which is Mi, which can be written as the number of moles times the molecular weight. And when you sum that over all I, the number of moles, you can write Ni as N times Xi, which is the mole fraction. So this sum can be thought of as being the molecular weight of the mixture, because it has exactly the form that M is the total number of moles times that quantity W. So W is the mixture molecular weight. I said that there must be a relation between mass fraction and mole fraction, and you can obtain this from the fact that the mass fraction is Mi divided by M, and the mole fraction is similarly, but it's Ni divided by N, and then when you replace, when you introduce the molecular weight, then you obtain the following relation that relate Yi to Xi. Okay, so the mass fraction Yi is the mole fraction times the molecular weight of the species I divided by the molecular weight of the mixture W, which brings into an interesting relation that unlike the mole fraction, that when you sum them, multiply by the molecular weight, you get the total mixture molecular weight. When you use the mass fraction, it's the ratio that end up to be 1 over the molecular weight. So the relation to the mixture molecular weight is different. It can be expressed or summarized here in this relation. It's important to remember or to know that. Okay, I'm sorry, there are, of course, many steps here that if I was in a semester classroom, I will derive them on the board, but here I rely on you reviewing that later and identify those things. Where did I go? Okay, here I am. So now we want to start using those ideas to write equation for mass, momentum, and energy conservation for the mixture. So we start with the mass balance of different chemical species. So we assume that in the mixture there's a species I, for example. It has, we know the mass, we know that that species move at some velocity which identify as VI. So VI is the velocity of that species. Say the species are colored blue, red, orange, so the blue move at some velocity VI, the red move at a different velocity VI, and so on. And the density of the species I can be written as rho times yi from previous slides. And so we can write similarly to what we used before as the mass conservation, that the time rate of change of the density rho I, which is rho yi, plus the divergence of rho vi, rho I vi, which is rho yi vi. But now species I, the mass of species is not conserved. And so there may be a creation or a production or some are destroyed, some are created. And so the rate that this is produced is denoted by omega I, and of course per unit volume, per unit time. And so the change in mass is proportional or is equal to omega I. And this is true for each species I. Now, I said that each species move at a different velocity, but the bulk move also at some velocity. So VI move relatively to the bulk at a velocity that we refer to as a diffusion velocity, and I denoted it by capital VI. So species I move at a velocity VI relative to the bulk, which move at a velocity V. The bulk move at a velocity V, which is defined proportionately to the mass fraction. So V is yi VI by definition. It's essentially the mean velocity of the mixture. And so when we use the diffusion velocity to replace the specific velocity VI, the equation then can be written as written here. Okay, so it's essentially recasting this using the fact that VI is the V plus VI, okay, equal to omega I. Now remember that the sum of yi must be equal to 1. So when you substitute, when you sum this equation over all I, since the sum of Vi times Yi is going to be equal exactly to V, the sum of Yi times the diffusion velocities is equal to 0. So it's an important constraint. Essentially, it's a constraint that mass is preserved. It's not disappearing. Okay, so this is the mass conservation. I rather use the word mass balance because it's not conserved, strictly speaking. So it's a mass balance for species I. If we sum this equation for all I, we get the conservation equation of the mixture, the mass conservation equation for the mixture. So clearly, when you sum that up, clearly the sum of omega I is equal to 0, but this is a statement essentially that mass during chemical reaction, it's neither total mass, it's neither created or destroyed. In other words, species change identity, but there is no more mass into the system. Okay, this is one more comment that I want to make, which comes here. So here again, it's the mass conservation of species I, and then we can use essentially the product law to change the derivative of the product rho I into rho dy I dt plus yi d rho dt, and similarly the divergence into this term and that term. And then you notice that there are two terms here. That's a mass conservation of the mixture that is equal to 0. So the equation for yi can be written in that form. The difference between those two forms is often referred to as conserved form or not conserved form. Not exactly, but in that sense, I will maybe point that out later. So when you sum all this, for all I, you should get the total conservation of mass. So there is some redundancy here, clearly. So essentially, there are only n-1 equations on top which are independent, okay? Because there's always the last yi is the 1 minus the sum of all the n-1. So you cannot use in practice to solve both this equation because there is a redundancy here. So if you use the total conservation of mass, you use only n-1 of those. Okay, otherwise you may get some inconsistency in your calculation, perhaps. It can be used as a verification, but not other than that. Okay, next thing is conservation of momentum. So that's a bit more complicated, and the whole idea is you write momentum equation for each species, and again you take the proportionate amount that you have, which is yi, and you create a sum of all the individual momentum equation into one global momentum equation for the mixture. And what you get is something very similar to what you have for a pure substance, which is, again, mass times acceleration, the pressure term, the viscous term, or the viscous stresses, and here is the body force. But now, in general, if only body force is gravity, gravity acts on all the species equally. But sometimes there are other body forces that can act on some species and not others. For example, when Fi is, so that's why there is an Fi, which is the body force on species I. For example, if you have electrical forces which would act on charged particles, such as ions or molecules or electrons that are often produced by chemical reaction, they would have a different body force than other species that are not electrically charged. So if that's an important item that you are investigating, then you have to pay attention to that term, okay? If Fi is only the gravity, then G can be pulled out of the sum. The sum of yi is 1, and so then you get the standard rho times G term there, or rho times F. Okay. The other thing to point out is that the viscosity mu is going to be some kind of average viscosity, or it's going to be a viscosity of the mixture. And in the literature, there are different versions of computing them and so on. I will not get into this. And by the way, when you sum all the equation, the momentum equation, different I, you're going to get also here a sum of Pi, which is written as you see as P. So Pi are essentially the partial pressure, and the fact that P is the sum of all the partial pressure is known as Dalton's law, and it's essentially used, or if you like, produced in this relation. Okay, I think I pointed out to most of the things here. We have to move on. So we go to the energy equation, and again we're going to write it in terms of the total energy. Again, that equation is obtained by writing individual equation for all the species I and then summing them up. which is not a trivial step, but, and I'm sure that there are also questions that one can argue about certain terms, how to do it, and so on. So that's left for a different discussion. So what you get now is an equation which is very similar to what we had for a pure substance, the rate of work done on the fluid by surface forces, the rate of heat transfer to the fluid, and finally the rate of the body force. But now if I left the Fi not all equal as I did before, or as I mentioned before, then that term can be written as Yi Fi, and I replace the Vi with the velocity of the mixture and the diffusion velocity, okay? Okay, so this is for here, and the next step is, as we did before, we want to extract from the total energy the kinetic energy, right? So when we extract the kinetic energy, and I will skip the detailed steps, you end up with an energy equation that involves the internal energy E. So rho times dE dt is the pressure term, very similar to a pure substance. You have the viscous dissipation. Phi is very similar to before. The only difference is that the viscosity coefficient is now of the mixture. And you have the heat transfer to the fluid element, and you have the body forces which depend here on the different Fi and Vi. Note, by the way, that if Fi are all the same, let's say if it was gravity, then it can be pulled outside. And remember that Yi Vi is equal to 0. It's one of the constraints, and so that term goes away. Okay? And here is a summary of those equations, where the emphasis is that there are few things that remain to be determined. First of all, E and P are thermodynamic quantities that we have to discuss separately because now they are for the mixture. Q and Vi are transport quantities, that's the heat and diffusion, and we have to talk about different laws that were appropriate for a mixture. And omega I, which is appearing here, the chemical kinetics, okay? We will start with thermodynamics, and I will, I don't know, when did we start? We started at 8:45, 9, never sure of those times. Let me go on with a couple more slides, and then we'll take a break. I will have also to accommodate the lecture as we go along, because I always have more than what I can speak about. So I will have to occasionally cut or decide what to do. Okay, so the state of the mixture, unlike a pure substance, is now dependent on the n fluids plus 2. So it's 2 plus n, but really n minus 1, because there are only n minus 1 independent quantities. Remember, the sum of all of them is the mixture parameters. So it's n plus 1 parameters. So if we assume that all the species behave like ideal gases, then Pi is rho I RT over Wi. And if you use Dalton's law, or the sum of Pi is P, then you can write the equation of state as P rho RT times the sum of, remember, rho I is rho times Yi, so you have Yi divided by Wi, which we noted before, it's 1 over the molecular weight of the mixture. So it's rho RT divided. So the equation is very similar to the equation that we wrote before, with the understanding that the molecular weight is the molecular weight of the mixture, and in principle it varies because it depends on Yi, and Yi change over time, and so molecular weight change over time. Often we assume, and we will assume in this lecture that it's constant, but it's not an obvious assumption. It's not immediate. Okay. The next thing is we want to introduce specific heats. So we talk about the enthalpies HI of each species. And if we integrate the relation, remember the enthalpy is related to the internal energy like before by E is H minus P over rho. So you just put an I for each species. When you integrate this, you get a reference enthalpy HI naught plus the integral of CPI. So CPI are the specific heat of each species. Note that the reference now, there are many references, HI for each I, so we cannot just choose them independently. There must be some consistent way of choosing this, something that I will talk about in a few minutes. The next thing is the internal energy EI can be written as EI naught plus the integral of CVI dt. And of course, HI and EI, the reference value are related, so really one have to focus only on one of them, which is HI naught. Then we can talk of the specific heat of the mixture, which is again summing over all the species by the mass weight YI. So CP is the sum of YI, CPI, CV is the same. And one can also write the enthalpy of the total mixture and the internal energy of the total mixture by just summing YI, HI, and YI, EI. And so you have those relations. This one is an important one that we will focus on because we want to use the enthalpy as the quantity to write the internal energy with. But note that there is a relation similar to before between enthalpy and internal energy of the mixture, so that's that. And the enthalpy is the sum of YI, HI naught, which are the reference enthalpies, plus the integral of the CP. CP here is for the mixture. Okay. So how do we choose the reference enthalpy? So for each species, the reference enthalpy is chosen as the heat of formation of some at some standard temperature T naught. And the heat of formation is defined, the heat of formation is defined as the heat that evolved or is absorbed when 1 mole of substance is formed from its elements in their standard state. Standard state is the form which is the most stable one under room temperature and atmospheric pressure. So for example, C plus 2H2 gives you methane. So the heat of formation of methane is going to be actually found from tables to be, as you see, minus 4.68, minus because heat is produced when this is so. The point here is that C and H2 are the most stable one in the standard state, and so the heat of formation of CH4 is obtained again as the heat of the heat of formation is going to be essentially from the formation of methane. So this is now by definition. Things like H2, O2, N2 must have heat of formation of 0 because they are in their most unstable state, okay? But be careful, O, molecule O is not necessarily, it's one here. Here it is. It's not 0 because you need to break O2 to form 2O, and so clearly it's not 0. Also note that the heat of formation depends on the state of if it's gas or liquid. So for example, for water, if you produce gas, this is the heat of formation that you can read here. For liquid, it's a little different. Of course, the difference between the two is the latent heat of vaporization of water. So there is, of course, a consistency here. Anyway, I just pointed it out because I wanted to bring it to, perhaps it's a good point to stop. I wanted to bring it to your attention that we don't choose those reference value as we wish. We have to be consistent, and that's typically the way that it's chosen. And those heat of formation are tabulated, and so it can be found. Okay? So we will continue after that with diffusion, heat flux, and whatever is remaining.